So I hope everybody can see the slides. As I mentioned a minute ago, this is a study that we conducted at MIT with a group of faculty and students, both graduate and undergraduate students. It lasted 2 years, between August 2016 and August 2018. We released the report in September, and since then we've been on a bit of a world tour to present the findings, and there has been certainly a lot of attention. I think the study and the report came out at a time of transformation for the nuclear industry. Some things are better than they used to be, others are more challenging, and particularly the economics, as you will hear in a few minutes. But we hope that our analysis shows that nuclear does have an important role now and going forward, particularly as the world seeks to decarbonize its energy sector. And that's really sort of the bottom line message of the study, is that the main opportunity for nuclear to grow and to play an important role on a global stage is decarbonization. So let me move on. We have looked at essentially two questions. The first is, everybody knows we have currently a large fleet of nuclear power plants, and the first question is, what do we do with it? As I'll explain in a couple of minutes, not the majority, but a significant fraction of these nuclear power plants are coming to the end of their lifetime, so to speak, or at least the end of their license lifetime. And the question is, should there be an investment to extend the lifetime of the existing fleet, or is it possible to replace nuclear with other energy technologies? So that's the first question that we will tackle, is what is the value of the existing fleet of nuclear reactors? And then I'll switch gear a little bit and tell you about, okay, if we now look forward to the future, next 20 years, 30 years, should we build more nuclear or not? So that's how I'm going to sort of set up the conversation here. So the first statement is sort of a recognition of the fact, as of now, nuclear is by far the largest source of carbon-free electricity in important regions of the world, such as the United States and Europe, as well as Korea and others. You can see on this plot is essentially the total electricity generation from carbon-free sources. So the three sort of groups are nuclear, hydro, and then everything else, which is solar, wind, geothermal, biomass, and anything like that. And you can see on a global level, hydro takes about half of the carbon-free electricity, followed by nuclear at about 1/3, and then less than 20% for solar and wind. But as I said, in places like the United States or Europe or even the Republic of Korea, nuclear takes up already a much greater fraction. So it is a very much an important component of the electricity mix, of the carbon-free electricity mix right now. So let me move on. It's interesting also to look at the correlation, if you wish, between the use of nuclear, hydro, solar, and wind to the carbon intensity in the power sector. So I'm going to define carbon intensity in a minute, but first, let me explain what you're looking at now. These are obviously, as you can see here, the list of European countries, and they are ranked according to the share of essentially solar and wind generation over a period of a little bit over 1 year, between 2016 and 2017. This is not capacity, this is actual generation. Over that period of time, the average share of electricity from solar and wind in Europe was about 20%. That's the yellow line that you can see here. And there were 6 countries that were at or above that average. They are Denmark, Ireland, Germany, Portugal, Spain, and Finland. These, by definition, are the countries that have invested the most in renewable energy, particularly solar and wind. The next plot here shows the same countries, all the Euro countries, but now they're ranked according to their carbon intensity. Carbon intensity is the amount of CO2, carbon dioxide, that is emitted per unit electricity generated. So the figure of merit here is grams of CO2 per kilowatt hour. And you can see that the 6 countries with the lowest carbon intensity in Europe are Norway, Sweden, France, Switzerland, Finland, and Belgium. So if you compare the group of countries that have invested the most in solar and wind and the group of countries that actually have achieved the lowest carbon intensity in the power sector, you can see that there is basically no correlation. The only country that shows up in both groups is Finland, and Finland actually gets most of its carbon-free electricity from nuclear and hydro. So it's almost like the exception that confirms the rule. So the message here is that, at least looking at Europe, which is an important experiment with many different energy policies, some completely at odds with each other, but with an integrated continental grid, the conclusion really is that, looking at the data, is that low carbon intensity correlates very well with the use of nuclear and hydro. The 6 countries that you see down here in green heavily use either nuclear or hydro or both. Let me move on to the next slide. So we do have this fleet of nuclear power plants, and in many cases, these plants are approaching the end of their original license. You may know that nuclear power plants are typically licensed when they're built to last for 40 years. There is now a trend, I think, worldwide to extend to 60 years. That has happened extensively in the US. It's probably happening in Europe and in Asia. And actually, here in the United States, we also have a few plants that may extend from 60 years to 80 years. But the question is always, once you get to this sort of decision point, the question is, are we going to decommission or are we going to extend the license? So if you decommission, there are certainly some, some downsides to this. The first is you lose the jobs and tax revenues that are generated by these plants. This is particularly important for plants that are built in areas that are economically not particularly developed, particularly the states here in the US or regions of Europe, they place high value on the fact that nuclear power plants employ a lot of people. These are well-paying jobs, and they also pay a lot of local taxes. So you're going to lose that. And we have examples here in the US and elsewhere of carbon dioxide emissions increase if nuclear power plants shut down. In the US, we had, as of now, 3 or 4 plants that have already shut down: Vermont Yankee and San Onofre in California, Vermont Yankee obviously in Vermont. And when those plants were shut down, the emissions, the annual emissions in the power sector of those states went up. This is fairly obvious to understand. If nuclear plants are shut down, they're typically replaced in the US by natural gas, in other countries by natural gas and coal, in other countries maybe by a combination of solar, wind, and natural gas backup. The bottom line is that whatever you replace a nuclear power plant with, it's gonna increase the carbon emissions, because the mix that you put on the grid is not as low carbon as a nuclear power plant. So that's what happens if you decommission a plant. What if you decide to extend the license? So extending the license of a plant is not free. There is an investment that is needed. Some components may have to be replaced, retraining a workforce, and so on. And the key question then becomes, will the plant be profitable? Will it continue to be able to make money? So we did 2 calculations or 2 analyses, one for Europe and one for the US. The one in Europe is Spain. Spain currently has 7 reactors, which generate about 7 gigawatt of electricity. And they're going to come to the end of their initial license in the next decade, between 2020 and 2030. And the question for Spain is exactly what we said a second ago. Am I going to decommission these plants and replace them with something else, or I'm going to make an investment and extend the lifetime of the nuclear power plants by, say, another 10, 20 years, 30 years, whatever is appropriate. So the analysis that we did is an economic analysis, and we compare the scenario where all 7 nuclear power plants in Spain are renewed, to a scenario in which all the reactors are shut down and they are replaced by a combination of renewables, and in this case batteries, because Spain has very ambitious and aggressive targets for decarbonization. So replacing nuclear with natural gas there, at least in the government's eyes, is not an option. So they say, okay, if we shut down nuclear, we're going to replace it with renewables and batteries so that the emissions do not go up. And here you see that there are, in fact, 4 scenarios without nuclear. The first we call it S7, which means all 7 nuclear power plants are replaced by solar power only. W7 means they're replaced by wind power only. And then SW7 and WS7 are replaced respectively by 25 and 75% solar and wind. So those are the scenarios that we looked at. And the key results of the analysis are shown here. If you invest in the nuclear power plants, it's going to imply, or it's going to cause an increase in the average cost of electricity in Spain by about 35 euros per megawatt hour. So, as I said earlier, extending the lifetime of nuclear power plants is not free. But you have to compare that to the incremental cost of electricity in Spain if you shut down the nuclear power plants and replace them with one of the 4 scenarios here that are all renewables and batteries. And you can see that the best you can do in that case would be with 25% wind and 75% solar, which is this last scenario down here. And in that case, the increase in electricity in Spain would be about double what you would have if you decided to make the investment in the extension of the nuclear power plants. So those are specific costs, so it's euros per megawatt hour. But you can look at this also in terms of total cost of the country. So the difference between the nuclear and the no-nuclear scenarios, in the best case for renewables, would be about $8 billion euros per year for Spain. So you can view that as a fee that Spain would have to pay for the decision to decommission nuclear and replace it with renewables and batteries. So the bottom line message here is that for the case of Spain, and many other regions of the world look a lot like Spain in this sense, it is actually economically more attractive to extend the lifetime of the existing nuclear power plants rather than replacing them with renewables and storage for the same amount of emissions. So that's kind of an important message. Let me move on to the next slide. This is the calculation for the United States. I'm not going to get into the details here. In the US, the issue is not necessarily the extension of the lifetime of the nuclear power plants, because in some cases they've already been extended by 20 years. The issue in the US is that many nuclear power plants, particularly in deregulated electricity markets, are losing money. Essentially, they're producing electricity at a cost that is slightly higher than the price of electricity in that market, okay? And so they are unprofitable. So in the case of the US, again, without getting into the details of this graph here, we calculated that a credit, it's called zero emission credit, given to nuclear power plants in the amount of between $12 and $17 per megawatt hour would essentially make our entire fleet of nuclear power plants profitable, and it would allow it to, therefore, to continue to operate for the next 20 years. Similar calculations have been done by individual states in the US, New York, Illinois, New Jersey. They have reached the exact same conclusions, and so in those 3 states, as of now, again, New York, Illinois, and New Jersey, the nuclear power plants are actually receiving a small subsidy of between 12 and 20, or between 15 and 20, I think, dollars per megawatt hour to ensure that they are profitable and they can continue to operate. This is done in the name of avoiding emission increases that would be certain if you shut down the plants and replace them, as I said, with other capacity. What's been interesting in the US is that this approach to essentially rescuing the existing nuclear power plants has been endorsed also by some organizations that traditionally were very skeptical of nuclear. You might have heard of the Union of Concerned Scientists, not an explicitly anti-nuclear organization, but always sort of on the negative side of nuclear. Well, just a few months ago, they came out with a surprising and very strong statement, a report actually, that delineates their new position on nuclear. And they basically saying is that we need nuclear to address climate change and to reduce carbon emissions in our energy mix. And more specifically, they endorse the zero emission credit approach that the different states are implementing in the US. So this is a very positive change in attitude, and I think people are starting to recognize that nuclear already is playing and can play an important role in decarbonizing the power sector. So that's the discussion that we've had so far is about the existing fleet. Now, if you look down the road over the next 20, 30 years, the question is, do we need to build more nuclear? And so here we're now talking about deep decarbonization. You see, it's actually fairly straightforward, particularly for countries that start with a mix that is highly carbon intense. Emilia is from Poland. Poland uses a lot of coal. They have very high carbon intensity in their power sector. For a country like that, simply switching from coal to natural gas will significantly reduce the carbon emissions. Significantly means maybe a factor of 30–40%. You can also bring some solar and wind capacity online that will further reduce the emissions. But if you are interested in deeply decarbonize the power sector, which is very much needed if we want to ultimately address climate change, global warming, etc., then our analysis shows that you actually need more than just solar and wind, and certainly you need to ultimately get away from natural gas and coal. So let me explain what this slide is really saying here. The bottom line message is at the bottom of the, or 3/4 of the way down the slide. And basically what we found is that excluding nuclear energy in low carbon scenarios drives up the average cost of electricity. So if you don't have nuclear in your energy mix, the cost of achieving deep decarbonization is going to be much higher than if you allow a nuclear component to be part of your energy mix. So how do we reach that conclusion? We developed at MIT over the past 5 years a tool which is called GenX. It's essentially a simulation of power markets. It takes a region of the world. This could be a country in Europe. It could be a province in China. It could be a set of states in the US, and it simulates or models the power market in that region. So as input, it requires the hourly electricity demand, 8,760 entries, one for each hour of the year. It requires the hourly weather patterns, how much solar capacity and wind capacity you might have at any given hour of the year. And then it also requires input for the capital, operation and maintenance and fuel cost of all the power plants on the grid, as well as backup and storage. If you have solar and wind, you need either a natural gas backup or battery storage. And lastly, it requires ramp-up rates. How fast can a power plant come online when the demand changes? So that tool crunches all these numbers together, and basically it pulls out an optimal generation mix, where optimal means that the average cost of electricity in that market is minimized. So in that sense, it's optimal. And we can run that tool for different scenarios. The scenarios are shown here in different colors. So blue means nuclear is excluded from the generation mix. Orange means nuclear is allowed to play at nominal cost. And then gray is nuclear is allowed to play at somewhat lower cost. And we can run these different scenarios for different decarbonization targets. So the last sort of variable that you have to pay attention to on these plots is the x-axis, which is CO2 emissions. Again, grams of CO2 per kilowatt hour. I should say currently the world is at around 500 grams of CO2 per kilowatt hour average. And according to climatologists, we need to go down to definitely less than 50, actually much closer to 10 than 50 grams per kilowatt hour. Okay, so now let's look at these plots. On the left, you have one extreme, which is Texas. Texas has very cheap natural gas. It has very favorable wind and solar, a lot of sunshine, lots of wind, particularly in the western part of the state. So you can see that for the case of Texas, unless one is really interested in going down to super, super deeply decarbonized mix here, the difference between having nuclear and no nuclear is not very big. You have to look at the difference between blue and orange, and you see the average cost of electricity, whether you have nuclear or not, in a place like Texas, doesn't make much of a difference. But most of the world does not look like Texas. Actually, most of the world looks more like the plot on the right. The plot on the right is for the region around Beijing, densely populated, fairly expensive fossil fuels, particularly natural gas, not cheap there, and it's a high latitude, and so you get not a lot of sunshine, not a lot of wind. So in this environment, you can see that even at the modest decarbonization target, for example, 100 grams of CO2 per kilowatt hour, the difference between having nuclear and non-nuclear starts to become quite significant. And if you go down to 50 or 10 or even 1, the cost of electricity in scenarios without nuclear might be 2 or 3 times higher than the cost of electricity if you allow for nuclear. So in this kind of markets, nuclear can and should, I would argue, play a big role going forward if we are interested in decarbonizing and at the same time maintaining costs that are reasonable. Now,
if I may, a little comment from my side, because you mentioned absolutely. Poland, and then to many countries in Europe, actually, the security of supplies is also something very important. So we know that where gas is coming usually outside of Europe, and this is why it is very often not the option. Yeah. So nuclear is one of the solutions for the countries, especially the eastern part of Europe.
Yeah, Emilia, that's a good point. And our study really focuses on decarbonization, but there are, of course, other attributes of nuclear that are important. You mentioned energy security is one. I mentioned also the economic impact of nuclear, both direct jobs and taxes, as well as indirect in terms of technology proficiency of a country. In some countries like China and India, nuclear has also been pushed by the governments because they have a pollution and air pollution problem. This is not related to CO2, it's more related to the fact that if you burn coal, and in the case of India, they also burn a lot of biomass, you get a lot of particulate in the air, and that's causing a lot of respiratory problems to the local population. So, but your point is well taken. There is more to nuclear than its role in decarbonizing the energy sector. But that's what we focus our study on, and you will see it's a pretty powerful argument. So why are these trends as strong as they are? Particularly, take for example the Chinese case over here. So why is it that if I exclude nuclear, the average cost of electricity goes up? Well, if I exclude nuclear, and I still am interested in decarbonizing, then I cannot use natural gas or coal because they emit CO2. And what you're left with is solar, wind. The solar and wind, as we know, are intermittent. Sun doesn't always shine, the wind doesn't always blow, and therefore they require energy storage. And they require energy storage in amounts that are enormous, and therefore they cost a lot of money. So in this slide that you see now, it's the example of South Korea. The top plot shows both load, which means demand, and generation throughout the year in Korea. The thick, solid black line here is the daily average demand in Korea. So that's how much electricity basically they need at on any day of the year. And the shaded line is the electricity generation that Korea would get if 50% of its demand was met by solar and 50% was met by wind. So in other words, if all their electricity demand was met by renewables, this is sort of the generation that they would get. Now, as you guys may know, the electric grid has to be in balance at any given time. In other words, if the demand is X, the generation at that particular time has to be X. If there is a mismatch between these two, you need to either waste or store the excess energy. And if there is a deficit of energy, you need to basically provide it by other means, backup. So if you take the difference between these two curves, then you get the plot at the bottom. Oops, excuse me. Let me go back. You get the plot at the bottom, and in blue you have the excess generation, and in gray you have the deficit. And basically this tells you how much storage you're going to need in a place like Korea. Okay, so you have to pick the maximum or thereabout, and so you're looking at 80 gigawatts of storage for a place like Korea. 80 gigawatt for Korea is enormous because, as you can see here, the size of their grid from the from the solid demand here is actually about 60 gigawatt. So essentially, on top of the grid that you already have, you need to build more than the same capacity, or more than twice the same capacity, just for the batteries. Not to mention the fact that you already have to overbuild solar and wind because the capacity factor, or the amount of electricity that they generate, is not 100%, is much lower than that, particularly in a place like Korea. So it's really this enormous build out of, or overbuild, as I call it, of solar, wind, and batteries that drives up the cost if you don't have nuclear. So the ideal situation is to have nuclear plus solar and wind, and nuclear is very good at filling sort of the gaps for solar and wind. So that's what our analysis is showing. Let me pause here for a second and see if there are any questions about the decarbonization analysis that we've done for both the existing fleet and the looking forward to grow. This is a quiet crowd.
I don't see still any questions coming from the people. Anyone who wants to raise hand, guys? Okay.
We have someone.
Yes, I have two people. So Diletta, I unmute you now. Diletta Coletta Invernici, sorry. Okay, Diletta, please. Hello? Diletta? Could you put a question?
We cannot hear you, Diletta. Maybe you are on mute.
Okay, she put the question in written, so
okay.
I unmute her back. The question is, did you consider construction and decommissioning in the analysis?
Yes, very good question. Of course we did. You have to, because the cost of electricity is the total cost, is not just operation and maintenance and fuel. So for nuclear, but also for all the other technologies, we included the cost of construction, and for nuclear in particular, also decommission.
Okay, very good. Now I'm going back to, there is another person, Valentino Cosma. Valentino, I will unmute you now. Please.
Yes, hello. Yes, my question was when we saw the comparison between doing decommissioning or extending the life of the nuclear power plants. In your opinion, if we start decommissioning nuclear power plants, will this push to build new ones, or there will be no correlation?
I think in most cases there will be no correlation because the financial decisions are somewhat independent, but there are exceptions. For example, well, the two examples that come to mind are actually both in Europe. In the UK, the policy of the government is to replace nuclear with nuclear. So as the old AGRs, the advanced gas reactors that were built in Britain 30, 40 years ago are coming to the end of their lifetime, they will be decommissioned, and in that case, that will automatically open the door to new construction in the UK. And similarly in France, they have capped their total capacity to something like 56 gigawatt, or maybe higher than that, I forgot. But there is a cap on the total nuclear capacity in France, and there too, for new nuclear plants to be brought online, the policy is that older nuclear plants have to shut down. But with these two exceptions, for example, in the United States, the the decision right now is whether to decommission or extend the license. The question in the US, at least as of now, is not, do I want to build new nuclear power plants? Because quite frankly, with natural gas prices as low as they are in the US, nuclear would not be cost competitive. Unless, again, as I explained a minute ago, the decision is that we want to decarbonize further from where we are now. The current Trump administration is not interested in that, but maybe the next administration might be interested in which case a new nuclear, might be again on the table. Does that answer the question?
Yeah, thank you.
Okay. Good questions. Emilia, if there are no other questions on this, let me move on because I'm aware of the time. I want to now tell you, this is going to be a little bit more technical. If we were to build new nuclear power plants, what would they look like? So this is the topic of advanced nuclear technologies. In the study, we analyzed essentially every new nuclear reactor concept out there. There are the so-called small modular reactors. They almost invariably are based on light water reactors, either PWRs or BWRs, but they're smaller and they can be built in maybe in factories, which theoretically could reduce the cost. And also from a financial point of view, it's a little bit easier to build smaller plants than to build larger plants because the capital and risk is lower. Fairly proven technology, even though it has not been demonstrated at this small scale extensively, but you're talking about PWRs, BWRs, and so all the materials, all the fuels, all the components are essentially proven from decades of operations in existing plants. So that's the first category that we looked at. The second category would be the Generation 4 systems, and in our evaluation, of the 6 or plus different concepts that people are investigating within the Gen 4 group, the one that has the most promise and it is basically ready now is the high temperature gas cool reactor. So this is a very different beast, so to speak, from PWRs and BWRs. The coolant here is not water, it is helium. The fuel is not uranium dioxide in pellets with zircaloy cladding. It's actually so-called triso particles. So these are ceramic particles made with carbon and silicon carbide layers. They tend to be very, very robust. They can basically retain the fission products, even though the fuel experiences extremely high temperatures. And in the sort of illustration that you see here on this slide, the power conversion cycle would not necessarily be a Rankine cycle, a steam cycle, but it could also be a gas turbine. So you can achieve higher efficiency of conversion from heat to electricity, and the reactor has a very interesting safety profile. There are, of course, other Generation 4 systems, but we judge those systems not to be ready now, the same way that high temperature gas reactors and small modular reactors are. So our analysis has focused mostly on these two groups. Now, traditionally, you know that nuclear has been used for base load electricity. Pretty much that's the only application that we've seen other than propulsion in naval reactors, submarines and carriers. But in the civilian domain, they've been used for baseload electricity. What's interesting and exciting about these new technologies that are now being considered is that they offer, or they open up, a richer set of potential missions. So you still have, of course, cheap electricity generation. Because of the presence of renewables, all new nuclear power plants are probably going to be expected to be flexible operation capable, which means, being able to follow the load to an extent. But what's interesting in particular about the high temperature gas reactor is that now you can think about coupling a nuclear reactor not just to the electric grid, but also use the heat at high temperature for industrial applications. And so things that come to mind could be the production of chemicals that require heat at 500 or 600 degrees C, or even the production of synthetic fuels for transportation. So hydrogen is being considered, of course, for fuel cells, cars, and hydrogen is not a primary energy source, so it has to be produced using a primary energy source, and you could do it with nuclear, but it's done efficiently if you have a nuclear reactor that operates at high temperature. And other emissions that are listed here, desalination, it's a fairly small market. It's big in certain countries, but overall globally small. Nonetheless, of course, nuclear can help with that, depending on the technology, the reverse osmosis or some thermal system for desalination, nuclear can do it. And then last but not least, one area that I'm becoming more interested in is off-grid applications. So there are, for example, remote communities in the Arctic or in deserts, mining operations or military bases or some microgrids and so on. These applications do not require hundreds of megawatts, but they do require maybe tens or maybe even less than 10 megawatts of heat and electricity. And to satisfy that demand, you need smaller reactors. They're called microreactors, and they could be based on, again, LWRs or high temperature gas reactor technologies. And while overall these markets are niche, they are small, they may be an important entry point for these new technologies, because in these markets usually the competition is not very cheap natural gas, but it's fairly expensive diesel engines, and so you can afford to have a nuclear reactor that is a little bit more expensive because your competition is not as cheap as if you are connected to the grid. So that's sort of the the promise. We did look at the nuclear heat potential in the United States. You can see here a list of applications: refineries, chemicals, minerals, pulp and paper, and others. And we used several filters, I call them. Essentially, we look at the EPA, Environmental Protection Agency database for U.S. sites, U.S. sites that would emit a certain amount of carbon per year. Sites that would require a significant amount of heat, say 150 megawatts, and we made the assumption that nuclear heat could be delivered at maximum 650 degrees C, which is consistent with a high temperature gas reactor technology. And basically, by applying these filters to all sorts of industrial plants in the United States, we found that nuclear could capture today about 150 gigawatts of heat, which is significant. It's a relatively small fraction of the total heat market, but it is significant in absolute terms. And again, this does not include the use of nuclear for synthetic fuels or hydrogen for transportation. In that case, you would need a lot more than this. But it was interesting to see that even now, nuclear could penetrate these heat markets quite effectively. Let me move on. The other value that these new technologies bring to the table is their safety profile. What's shown here is an aerial picture of the Fukushima site. Fukushima, unfortunately, has changed the perceptions about nuclear energy in a negative sense, obviously, once again. If you look at the actual radiological impact of Fukushima on the population and the environment in Japan, is minimal. This has been studied at this point extensively by the United Nations. But from a social point of view, the disruption has been massive. You may know that about 200,000 people were forced to evacuate. That was not a good decision, but it did happen, and it has turned a lot of people against nuclear. So going forward, as we design new technologies, I think we have a new set of goals in the area of safety. For the existing nuclear power plants, let me say a couple of words about those. For the existing fleet, the big lesson learned from Fukushima was that you have to be able to cope with a station blackout without damaging the core. And there has been a lot of activity in retrofitting existing plants with additional equipment and additional energy sources that would allow to basically extend the coping time for a station blackout at the existing fleet, and that is taking care of at least the existing fleet. But as we look now at these new designs, I think you want to be able to demonstrate that there is no need for intervention from operators for infinite, I put it in quote, for a very, very long time during a station blackout. And even more important is you need to be able to show that even if there is a significant accident or severe accident, as we call it, the need for evacuation of local residents is eliminated. And what it really boils down to it is how effective the system is at retaining the radionuclides that are released or that are present during severe accident. So the existing, the two options that I mentioned, the high temperature gas reactor and the small modular reactors, actually do bring a very, very interesting safety profile to the table. So they all have what we call inherent safety attributes. In HTGR, there is no coolant to boil, so it's you don't run out of coolant because it cannot boil off. The fuel, this is absolutely key. The fuel has very, very high retention of fission products, even under the most horrendous postulated events. There is a very high thermal capacity in the core or in the system for both small modular reactors and high temperature gas reactors. So the system is able to absorb a lot of heat without exceeding temperature limits. And the reactivity coefficients, sort of the inherent neutronic features of the reactors, are such that the plant shuts itself down if something goes wrong. If you couple that with engineered passive safety systems that do not require AC power and other intervention from outside, you now have, we concluded that these new technologies basically allow you to eliminate the need for emergency power, at least safety grade emergency power, extend the coping times for station blackout enormously. They are all much simpler to operate, which is good in terms of reducing the number of initiating events. And last but not least, the source term of radionuclides is such that even under severe accident scenarios, we think that the emergency planning zone, so-called evacuation zone, could be limited to site boundary, which means by definition, local residents will not have to be evacuated. This set of attributes is being discussed in the US with the NRC. The NRC is our safety agency, nuclear safety agency. Within the context of the design certification of NuScale, NuScale is a small modular reactor based on PWR technology. And the NRC is indicating a very strong willingness and openness to value the safety attributes of these new reactors. So I think I'm hopeful that within a couple of years, we'll have a design certification for NuScale here in the US that essentially recognizes these good attributes for these new technologies. Let me come to an end by telling you a little bit about how to reduce cost of nuclear going forward. I showed that economic analysis at the beginning. It makes certain assumptions about the cost of new nuclear. There was a question about construction and decommissioning. They're all included, but of course we had to make some assumptions on what those costs are. And the current practice in the US and Western Europe, if you look at some of these new construction projects, they are too expensive. They're taking too long to build, and even once they're built, they're just very, very expensive. So we spent a lot of time in the study trying to identify ways to reduce the cost of new nuclear. And some recommendations are obvious, others are less obvious. So let me just very quickly walk you through this one. First, the first is kind of obvious. A lot of the cost of nuclear is about re-engineering the plant for site-specific requirements. So you change, the plan is nominally the same, but if you change site, you're going to have to do different engineering. And often they're built in 1 or 2 units at most at a site. So the first recommendation is standardize and build multi-unit sites. The more units you can build at the site, the better. From an economic point of view, there is very strong evidence that the first time the workforce builds the plant, it takes a certain amount of time, a certain cost. The second time they do it on the same site, the same workforce, the cost goes down and the time becomes shorter. And the third time even lower, and the fourth and the fifth. So this idea of having standardized series of reactors built at the same site is powerful, and it can really reduce costs quite dramatically. The other 3 recommendations for cost reductions are more technology-based. So the first is a lot of the cost in nuclear is associated with civil works, with reinforced concrete structures. And so reinforced concrete is is sort of a well-known material, but it is labor-intensive and it's costly because it requires arrangement of rebar, assembling of formwork, placing the concrete, and then removal of the formwork. So there are ways to reduce the number of steps and therefore the labor and cost associated with reinforced concrete quite dramatically. One way is shown here is to use steel plate composites. Another way is to use ultra high performance concrete or high strength reinforced steel. So in the report, if you care to learn more about this, we basically discuss how these innovations in concrete technology could help reduce the cost of new nuclear. Modular construction and factory shipyard fabrication, very important. Instead of assembling things at the site, which is expensive, push as much labor and as much work to factories and shipyards, which are very productive and cheap, and then bring large modules to the site and essentially connect them together. Again, has been done in other industries and with great results in terms of cost slashing. Lastly, seismic isolation. The idea here is to put the reactor on base isolation, on little shock absorbers. It's called seismic isolators. This, of course, increases the cost in a way because you need to pay for the seismic isolation, but it allows you to reduce very significantly the robustness of the structure that you put on these seismic isolators. So there is a trade-off there. You pay for the seismic isolation, but the structure that you put on top is going to cost less. And we found out that that trade-off is in your favor for virtually every site with a peak ground acceleration above 0.2 G, which essentially is almost all sites worldwide. So what's interesting about these recommendations is that they are applicable to all new reactor technologies, whether you like, PWRs, BWRs, high temperature gas reactors, sodium, whatever it is. These are recommendations that you can use in all those cases, and hopefully the cost will come down. Okay, I already said this, so I can skip. And let me just close with, let me see, this is the last one. Okay, let me close with this one. This is a comparison that we made between the nuclear industry and many other industries of similar complexity. So you see here, you have nuclear plants, coal plants, offshore oil and gas, chemical plants, satellites, jet engines, pharmaceuticals, automobiles, robotics. And we group these different industries according to 4 categories. The first category is, what is the scale of the product that this industry is offering? So in the case of a nuclear plant, the product is the plant itself, which is large. But the same goes for coal plants, offshore oil and gas, chemical plants. These are all large structures. Second grouping, how extensive and rigorous is the testing that is required to receive a license to operate these plants? It's very high for nuclear, very high for satellites, for automobiles, for jet engines, for pharmaceuticals. All of this, if failures occur, they all have high consequences, and therefore they're highly regulated. The third group is, how are these products built? Are they factory fabricated with modular construction, strong supply chains, and things like automobiles, robots, pharmaceuticals, or jet engines, excuse me, they do have very, very strong supply chains, and they're basically made in factories. Last group is the one in white. It says, the product that I'm selling is a commodity or it has a high added value. And chemical plants, pharmaceuticals, robotics, automobiles, they're all high added value products. If, since we are among Italians, if I am interested in buying a Ferrari and you're trying to sell me a Fiat, I'm not gonna like it. I want a Ferrari. I'm willing to pay 3 times as much because that's the car that I want. It's not a commodity. But nuclear and other power plants, they're selling electrons, and electrons are commodities. They don't have different colors or different flavors just because they come from different plants. So what you see here, the message here is that to intersect these 4 groups, the only technology or the only industry that has all the negative attributes is nuclear. And so in a way, the challenge of innovation for nuclear is to move from the top left here, which is very bad, to the bottom right here, where it would be very good. So now you could have smaller machines, therefore less capital or risk, that are built in factories, They will still have to be obviously heavily regulated, but they might have safety profiles, as we discussed a few minutes ago, that allow you to do licensing easier. And lastly, they may be able to sell products that are not just commodities. So this goes back to the discussion that we had, or to the statements that I made about using nuclear heat for niche markets or for industrial processes. So again, I think what nuclear needs to be very, very successful is, I call it a new paradigm, to smaller serial build systems with a broader mission and a recognized low carbon value. So let me stop here. You already saw the cover of the report. It's available. You can download it freely. This is the team that performed the study. So it's a mix of faculty and students. At the bottom, you see our wonderful students that did a lot of the work here. These studies take a lot of time and take a lot of money, so we had to raise funds from sponsors. It was mostly sponsored by the Sloan Foundation, but also EDF, Shell, and you can see other donors. So this is sort of the, I call it the Twitter slide of our, for our study. It summarizes in 4 sentences what the study is all about. We think that for nuclear, the opportunity going forward is its role in decarbonizing the power sector. The problem that we see for both the existing fleet and the new plants is cost has to come down. There are ways to reduce it. One thing I didn't cover is how can the government help, but there are ways in which the government can help. So let me stop here and take any residual questions that you might have.
Thank you very much. It was a very extremely interesting presentation, also for me, even if I saw it, some of the slides already before. I have a question here coming from Alfredo Portone. Alfredo, I unmute you now.
Can you hear me?
I can hear you fine, Alfredo. Yeah.
Thank you very much for this very interesting presentation. I have just a desire. Is this available? I mean, can I download these view graphs? And
yes, I can. I can make them available to Emilia and Antonio, and then they'll decide how to share them with you. But yes, at this point, everything I've shown is public information. So yes.
Okay. Thank you very much.
Following Alfredo's question, do you agree to, because I'm recording this webinar, to use this record to our ENS webinar YouTube?
Emilia, you can do whatever you want with the recording. As you know, I've been giving this presentation several dozens of times, and so the information is fully public. So yes.
Okay, there's another question coming from Valerio. Valerio Mascolino, please. Valerio? Okay, see, he wrote a question. No microphone. Okay, Valerio, could you provide your opinion on the way the nuclear professionals can impact policy making and make these changes and innovation suggestions real?
Yes, absolutely. One of the most exciting observation I've made over the past 5 years is that when I was a student, both in Italy and then even here at MIT, and even during the first few years of my career as a professor at MIT, the typical mold or the typical attitude from students was, I'm going to get a degree and then I'm going to go work in a company or in a lab, and I'm going to be a researcher for the rest of my life. And over the past 10 years, I've seen a radical change from that sort of model or that approach to one in which the students want to be, and therefore then they become young professionals out in the real world. They really want to be active agents of change and advocates for nuclear. And this has taken different forms. So at least I can speak about the experience in the US. I think Emilia and Antonio can tell you more about Europe, because that's very much what they do. But in the US, we've seen actually a significant number of students creating startups for new nuclear technologies. This can range from a new nuclear reactor design, which of course is very ambitious. Ultimately, you probably want to hand these off to a bigger company, all the way down to small innovations in nuclear instrumentation or things of that type. And so, but in all cases, I like to see the the enthusiasm, the courage, and really the initiative of saying, okay, I have a good idea for a new technology or a new approach, and I'm not just going to sort of wait for industry to do something about it. I'm actually going to create a company, go out there and do it myself. And of course, like all, this is not specific to nuclear, like all startups, some are successful, others are not necessarily successful. In the end, I think the fraction of companies that will become fully commercialized might be small, but if you don't take that risk, you're never going to have success. I should mention that NuScale, for those of you who are following, NuScale, which at this point is the most likely small modular reactor project in the US and worldwide to go forth in the next few years, was actually created by a university professor at the Oregon State University and his students 15 years ago. So it is, and NuScale now has grown to 450 people and has been acquired by a big company called Fluor. So there is a path to success. Anyway, that's the first thing that I've seen, is that people are willing to go out there and create startups. The second path is, you were asking about policy. There are many think tanks or NGOs here in the US that are studying the problem of climate change or environmental challenges and so on. And they are typically based in DC, in the Washington DC area, because that's the political heart of the United States. And many such organizations have been hiring nuclear engineers and nuclear professionals, and they've had a dramatic impact because they testify in front of Congress, they network with congressional staffers, they produce white papers or policy statements that are then picked by decision makers and turned into law. And this is not it's not a pie in the sky dream. It's actually happening. I mean, some of the legislation that the U.S. Congress has recently passed on advanced nuclear, with support of several hundred millions of dollars, is actually has been very greatly influenced by the work of these young people. So I'm giving you a long answer, but it's an excellent question, and I see these two paths as non-traditional approaches to being active and being protagonists. Having said that, let me say also, the traditional approach of doing good engineering and technical work within technical organizations is perfectly fine. It's just, there are new ways to do to be protagonists as well.